Hi, my name is Tianyi Zhou, and today I will give you a brief presentation about the paper called Space Efficient Interior Point Method with application to linear programming and maximum weight bipartite matching. And this is a joint work with Cliff Liu, Zhao Song, Hengjie Zhang, and Lichen Zhang. In this paper, we study the problem of solving linear programming in a streaming model and propose some efficient algorithm to solve linear programming and its application. So let's start with the definition of linear programming. So given a constraint matrix A, vector B, and C, the linear program problem asks us to solve the following primal and problem and its dual problem. So interior point method can solve a wide range of optimization problems, including linear programming, quadratic programming, and semi-definite programming, but its computation cost is quite large. So comparing with vanilla IPM, robust IPM follows central pass approximately instead of exactly. So in this way, it can save the computation cost. Robust IPM is the backbone of a series of breakthroughs for linear programming and semi-definite programming in the last few years, including the current best algorithm for them. The most time-efficient implementation requires maintaining the primal and dual solution at the same time. And the current issue is that to maintain the both primal and dual solution for IPM algorithm, we need at least M space, where M is the number of constraint and N is the number of dimension. In this paper, we show that IPM can be implemented in a streaming fashion with only N-squared space. The main idea of this paper is that we propose a robust IPM framework that works only on the dual formulation of the linear programming. The streaming model implies that at each pass, we can query the ith row of matrix A and the corresponding of map vector B. And next, let's talk about how we implement the IPM algorithm with three different barrier functions in small space. So let's start with the log barrier function. To calculate the gradient and the Hessian in small space, when we read AI and BI, we can first compute the slack variable S, which equals to AI transpose times X minus BI. And then we accumulate AI divided by SI to the gradient of the log barrier function. And similarly, we accumulate AI times AI transpose divided by S squared to the Hessian of the log barrier function. So in this way, the exact gradient and the Hessian can be calculated without any error in N-squared space. Next, we introduce the gradient and the Hessian for hybrid barrier function, which is the combination of the volumetric and log barrier. We can see that it is quite similar to the gradient and Hessian for the log barrier function. The difference here is that we need to compute the sigma here. In the last slide, we have already shown that the Hessian can be computed and storing using N-squared space in one pass. So for the next pass, we can compute the exact value of the sigma with only N-squared space. So then let's introduce the gradient and Hessian for Lie Sit-for barrier function. We can see that the major difference is that we need to compute the Lewis weight W here, and it is non-trivial to compute it in N-squared space. The first issue here is that storing the vector W has already taken N space, and it is M-dimensional. Also, when we compute the Lewis weight using an iterative algorithm, we need to update W by using this sigma, which also costs at least N space. So our idea is that we can introduce the variable Q to represent the inverse of A transpose WA, and it takes only N-squared space. The algorithm that computes Lewis weight is an iterative updating algorithm. It uses the Lewis weight from the last iteration to compute the new one. So what we do is that we use QT to compute WT plus 1 and use WT to compute QT. Therefore, we propose a recursive method to find the Lewis weight in small space. In order to compute this Q, we accumulate AI transpose WT for each I, and it also takes n square space. So we solve the linear program in square root n tau log 1 over epsilon passes and only n square spaces for an epsilon approximate solution. So next we're gonna introduce our result about in the small tree width setting, but before that let me first introduce to you what is the tree width. So here we first provide the definition of the tree decomposition. So a tree decomposition is a mapping of graphs into trees. So for graph G, the tree decomposition is defined as pure MT, where T is a tree and M is the bags labeling. It satisfies the following three rules. The vertices maintained by all bags is the same as those of the graph. And second, for every vertex in the graph, the nodes in the tree containing that vertex is a connected subgraph. And the third one is that for every edge UV in the graph, there exists a bag in the tree containing node UV. Let's see an example here. The first figure here is the dual graph of matrix A, and the second one is the tree decomposition of graph G. We can see that the union of the vertices in all bags of the tree are nodes A to I, which is the same as the union of all nodes in graph G, which follows the first rule. And for edge CB in graph G, bag 1 contains both E and B, and for edge EF, bag 2 contains both E and F. And for the third rule, we can see that the bags contain node C are bags 1, 2, 3, which is a subgraph of the tree. Next, we introduce the definition of the tree width. The tree width of a tree decomposition MT is defined as the maximum size of the bags minus 1. We can also say that the tree width of graph G is the minimum width over all tree decomposition of G. Here we can see that the maximum size of the bag is 3, so the tree width of the graph and the matrix A is 3 minus 1, which is 2. The intuition of tree width is that it can measure how similar a given graph is to a tree. And so the small tree width property appears naturally. In the NetLab dataset, most linear program instances only have tree width in the range from n to the power of 1 over 2 to n to the power of 3 over 4. In addition, the MetPower dataset, where the problem size is larger than 10,000, the maximum tree width is only 35. We first introduced the key of why small tree width can be leveraged to reduce the space cost. For any positive diagonal matrix H and A with tree width tau, we can compute the class key factorization of A transpose times H times A to L times L transpose in n times tau space and tau pass, where L is the lower triangular matrix and L is tau bars in column. In addition, given the class key factorization, we can compute L inverse times V in n space, where V is an n-dimensional vector. Therefore, given matrix A has small tree width tau, we can compute this leverage score in n times tau space and tau passes. Recall that for Lichen for barrier function, the key is to compute this equation in small space. Given the small tree width setting, we can use class key decomposition and rewrite it as the following. So using the lemma provided in the last slide, we can compute this leverage score in n tau space and tau passes. So finally, by using the techniques given in the previous slide, we solved the linear program in square root n times tau times log 1 over epsilon passes and only n tau space for an epsilon approximate solution. To summarize, in this paper, we give the first IPM that has no space dependence on the number of constraint n. In addition, we further reduce the space cost when matrix A has multiplicity with tau. We apply our technique to solve the bipartite graph problem. And due to time limit, this presentation didn't cover the bipartite graph problem part. If you are interested, please refer to our paper. Then this is the contact information. Thanks for listening.